Hello and welcome. This is module CM3292. It's the mini eLecture called Luminescence, and it relates to experiment 5A. The structure of the material is very much as on your screen, and in terms of references, I'm suggesting Skoog as a pretty much bulletproof basic analytical chemistry textbook. But if you're particularly interested in fluorescence and phosphorescence, I might suggest the Analytical Chemistry by Open Learning publication by Rendell, 1987, in your reference list. The style is absolutely not as open or readable as Skoog, and this is written as an open learning resource, which means that you get some information and then you get problems or questions around that information to encourage your learning. Okay, enough of that. We need to think about why we're sitting here. The aim of this and all of these mini lectures is not to brief you on the practical, nor how to use the equipment. If you think about it, you have got videos that show you how to turn the equipment on, do the measurements, get the data off, and shut down or sleep the equipment. So it's clearly not about that. And you've got a laboratory script which describes what you should be doing in the laboratory and how to do it sometimes. So this is not about that. This, like the other e-mini lectures, is simply to brief you on the underlying theory of the equipment, sometimes into the techniques you'll be using. It's worth noting that the basic theory of absorption has been covered, I imagine, at least once, maybe more than once, in your Year 1 and Year 2 lectures, so I'm going to pick and choose certain things to talk about. Practical 5A, which is this one, comprises of just the one mini lecture, Luminescence, this lecture. Okay, so let's think for a moment about the equipment and how it is set up to measure the phenomenon. So we start with a light source and a way of tuning that light source to give you specific wavelengths. That beam of light then goes through the sample cell, and if there were nothing else on this slide, pretty much that would be a UV visible spectrophotometer that you've already used many times. But in spectrophlorimetry, which is what this technique is called, there is another monochromator, a fluorescence monochromator, at 90 degrees to the light beam, and your sample cell has 4 optical sides rather than just the 2 optical sides for UV visible spectrophotometry. And then that emitted light is then measured. So luminescence, whether it be phosphorescence or fluorescence, involves the quantification, both in terms of wavelength and intensity, of the light emitted from a molecule after it has been appropriately irradiated, and during as well, actually. Okay, so that's, if you like, the definition of what we're doing, why we're here. So a solution, now that can be a liquid solution, or it can be a solid solution, one solid in another, is irradiated so as the ground state electrons are excited into higher energy states. What do I mean by that? Well, think as a chemist. The molecules in the sample are absorbing radiation, and so ground state electrons are being promoted up into higher excited states. Now we get to spectrophlorimetry, because as those electrons decay, they emit energy as light in two modes. First, fluorescence. We're going to talk more about these two in a moment, but effectively the electron returns to ground state very quickly. So you turn the light off and the fluorescence dies. The other mode is phosphorescence, which is much slower. So for phosphorescence, you turn the light off and it keeps glowing. So that means the energy of the emitted radiation is always less than the energy of the exciting radiation. And in terms of wavelength, of course, that means the wavelength of the exciting radiation is always lower than that of the emitted radiation. Okay, so obvious stuff. I hope you know very well already. Electrons have specific energies for a given molecule, and there are specific energy differences between different energy states in those molecules. Hence, if we are looking at persuading electrons to absorb energy, that exciting radiation must be at a specific wavelength which corresponds to the energy of the electron which we are trying to excite. Okay, so when you do UV visible spectrophotometry, the absorbed radiation has a sigmoid shape, because of course for every excited electronic level you have multiple vibrational levels which effectively give you a distribution of closely allied energies. Equally, the emitted radiation, whether phosphorescence or fluorescence, will also have a maximum intensity wavelength. Okay, again, stuff I hope you're very familiar with. So we have our little electron diagram on the right, and the leftmost diagram is a ground state where you have effectively paired electrons. Remember from your physical chemistry, maybe statistical chemistry, I'm not quite sure where you would have been taught it here. You have the fourth quantum number of an electron is plus half minus half. So in the ground state, in this diagram, we have a spin paired pair of electrons with an overall spin of 0. That tends to be called the ground singlet state. We then look at what happens when we add an appropriate photon of energy, and in the second part of the cartoon, that energy is absorbed by one of the electrons, and that electron is promoted to an excited state, but its spin has been conserved. Therefore, its overall spin is still 0, which means it's still a singlet. The other option, of course, is that the excited electron takes on the same spin, so it changes spin, which means that the overall spin quantum number is then 1 or minus 1. So whether you get fluorescence or whether you get phosphorescence is dependent on the overall spin after excitation. Now, absorption happens very quickly. 10 to the minus 14 seconds is a good average number. That's much, much less than the time scale of emissions. So whether you get fluorescence or phosphorescence actually depends on the overall spin after excitation, whether it's a singlet or a triplet, for instance. Now there are a number of deactivation fates, some of which involve the solvent possibly, some of which involve internal rearrangements, and we'll look at these deactivation routes in a moment. Okay, so here it is diagrammatically, and let's have a make sure we're happy with this. So we have at the bottom of the diagram the ground state, ground electronic state, with its associated vibrational states. So we add the photon, which is absorbed, and then the electron is promoted to one of the vibrational levels of the first excited state. Then, as in all of these cases, you begin to get vibrational relaxation. Whichever vibrational level the electron was promoted to, the energy cascades down through the vibrational levels, so it relaxes till it gets to the ground state, or the ground level of the first excited state. Now, it can be that there is internal conversion, which means we go from an S2 state to an S1 state. If that happens, again, we get relaxation via the vibrational levels until we get to the lowest vibrational level of the first excited state, at which point we can get fluorescence. And again, then in the ground state, we can the fluorescence may take the electron not to the bottom of the ground state, but some vibrational level above the bottom, and then you get, in the same way as previously, the degradation of the energy through the vibrational levels. So that's then internal conversion, which takes you, which gives you fluorescence. However, what can happen is, and it's particularly under certain conditions, that you can get what's called an intersystem crossing, where the energy states between S1 and T2 actually overlap and are very similar. In those cases, then effectively you get a change of spin, so you now have a triplet state, not a singlet state. There is then more cascading down, and then from the ground, from the bottom of the excited state, from the lowest vibrational level, you then get emission, and this time it's called phosphorescence. Now in all of these cases you can get internal and external conversion, which thwarts the luminescence, if you will, by cascading the energy down through the vibrational levels. Note, for fluorescence or phosphorescence, the light is always emitted from the lowest vibrational level of the first excited state. And so let's just be clear, for fluorescence, the electron returns to ground state quickly, less than 10 to the minus 5 seconds, and the spin is conserved. For phosphorescence, you get an intersystem crossing and a spin change, and the time scale of that can be seconds to minutes, which is why when you turn the exciting radiation off with phosphorescence, it keeps glowing. Okay. Let's take the most simple fluorescence example, which is resonance. and we'll have vaporized sodium atoms, and the 3s electrons are excited to the 3p state by shining radiation at 589.6, 589.0, that yellow colour that you see in street lamps. After about 10 to the minus 8 seconds, actually the electron returns to ground state and it emits radiation of those two wavelengths. So in this case, the emitted radiation is equal in wavelength and energy to the exciting radiation. So remember, we've just talked about transition from the lowest vibrational level of the excited electronic state. Mostly for fluorescence, you're looking at pi star to pi or pi star to n, depending on which requires the least energy. Energy is always minimized. Okay, the last part of this little mini e-lecture is going to be about fluorescence and structure. The most intense fluorescence is found with aromatic groups with low pi to pi star transitions. Remember, we're always looking for the least amount of energy. A few aliphatic alicyclic carbonyls and highly conjugated double bond structures can also exhibit fluorescence. Most unsubstituted aromatic hydrocarbons fluoresce in solution. So in terms of the type of structures from which you can expect fluorescence or expect to demonstrate fluorescence, that gives you broadly a guide. The intensity of fluorescence increases with the oxygenated degree of the species and with the degree of substitution. Decreases with halogens and decreases with molecular mass. Resonance structures increase the fluorescence. So effectively you're looking for large conjugated planar systems with some of these features. Then you can confidently or be more confident of finding a fluorescing system. And again, just reiterating what we've already talked about, the absorption is at the higher energy low wavelength, the fluorescence and the phosphorescence each increasingly lower energy and therefore higher wavelength. Okay, summary then, I don't think I need to read that to you. I think probably that's all I need to say. So, thank you for listening and enjoy the practical. Goodbye.